In 1995, astronomers found something that shouldn't have existed. 51 Pegasi b, a gas giant, bigger than Jupiter, yet circling its star in just 4 days. It was a hot Jupiter, a monster pressed so close to the fire that it snapped our picture of a proper planetary system in half. Then the floodgates opened. Thousands of exoplanets followed, and they looked like wild gardens. Giants wedged near their suns, chains of super-Earths packed tightly together. Compared to them, our solar system suddenly feels suspiciously tidy. 4 small rocks inside, a wide gap. Then, the giants standing guard in the cold. So here's the question I want to place gently in your mind. What if our system isn't just lucky? What if it was pruned? Think of an invisible cosmic gardener that cleared the debris, stretched the spacing, and nudged orbits into a long-term calm, just enough for a fragile blue world to take its time. There is no proof of intent, of course, but the evidence from Kepler and Gaia suggests that our quiet emptiness might be the rarest thing of all. So please, stay with me on this journey. We are about to look past the chaos and step into a vision of our home that is stranger, quieter, and more fragile than you've ever imagined. So let us walk in a little closer now. Not at the scale of galaxies or surveys or telescopes, but at the simple layout of home itself, as if you were standing at the edge of a dark yard and someone quietly turned on a light. If you could float above the solar system and see it all at once, it would not look like a random scattering of worlds. It would feel arranged. Inside, close to the Sun, there is a tight cluster of 4 small rocky planets: Mercury, Venus, Earth, Mars. They orbit in fairly neat circles, all more or less in the same flat plane, like stones laid carefully along a path. Farther out, there is a gap of mostly rubble and shards, the asteroid belt. And then beyond that, the giants rise: Jupiter, Saturn, Uranus, Neptune. Massive gas and ice worlds in the cold, spread out more widely, encircled by minor bodies and distant icy leftovers that form the Kuiper belt. It is as if someone planted smaller bushes near the house, taller trees at the edge of the yard, and then let the wild field begin. What is strange is not that there is structure. Gravity will always carve some structure out of dust and gas. What is strange is how calm that structure is now. The big planets move on, orbits that are close to circular, not stretched out into thin ellipses. They are not flung wildly up and down out of the common plane. For billions of years, no giant neighbor has barreled through to tilt everything sideways. It looks like a garden that had its storms long ago and then settled into a long, slow, almost patient stillness. At the center of all this is a star that is, in its own way, moderate. The Sun is not a very cool, dim dwarf, nor is it a blistering blue giant that burns through its fuel in a hurry. It is a yellow star of roughly middle mass and middle temperature, long-lived and, by stellar standards, reasonably well behaved. Its brightness does change with magnetic cycles and sunspots, but not so violently that climates on its planets are ripped back and forth between fire and ice every few centuries. In the vast catalogue of possible stars, the Sun is not the only one like this, but it sits in a category that is rare enough and steady enough to draw attention. Around this star, there is a ring of distances where liquid water can exist on the surface of a rocky world. Too close, and any oceans would boil away into steam. Too far, and they would freeze into permanent ice. Earth occupies a position inside this band that allows water to remain liquid over very long spans of time. Too close inward, Venus shows you what happens when a runaway greenhouse effect locks in. Too far outward, Mars shows you what happens when a planet is too small, too cold, its air too thin to hold on to warmth. If you were to look only at the three, it would be hard not to feel that something in the middle was being gently balanced. There is a temptation to imagine a dial. Turn it a little inward, and oceans vanish into steam. turn it a little outward, and they fall, silently, into solid crystal. Somewhere in between, for a long while now, Earth has stayed in the narrow band where liquid water can flow, freeze, evaporate, and fall again as rain. Not perfectly, not without ice ages and shifts and crises, but continuously enough for chemistry to have time to become biology, and for biology to become minds that can think about dials at all. When you look at the shapes of the planetary paths, another quiet oddity appears. In many chaotic systems, orbits bear the scars of their history. A planet that has been violently scattered will circle its star on a stretched, eccentric loop. A world that has been tugged and torqued by neighbors may tilt sharply out of the common plane. Yet the main planets here glide on paths that are nearly circular, their tilts small and similar. It is not that chaos never happened. The craters on the Moon, on Mercury, on Mars are testimony that it did. It is that, somehow, most of those scars are buried in the rocks themselves, rather than in the shape of the orbits. As if the soil was churned, and then, over time, leveled again. Then there is the missing layer. When astronomers catalogued thousands of exoplanets around other stars, they found a class that seems to be incredibly common. Worlds larger than Earth but smaller than Neptune, often called super-Earths or Mini-Neptunes. Many systems host 2, 3, or more of these planets, nestled in close to their stars, locked in tight chains. In our solar system, that entire category is absent. There is Earth, and then, instead of a series of larger rocky or puffy worlds stepping outward, there is a gap, and then Jupiter. It is like walking through a garden, where every other yard on the street has a row of mid-sized shrubs along the path, and yours simply does not. You do not notice that kind of absence until you start comparing. Once you do, it is hard to unsee. Why are there no super-Earths here? Why did this system end up with small rocky planets, then a belt of debris, then distant giants, instead of planets filling every available niche? Something, at some point, removed material from the inner solar system, or prevented it from gathering into larger worlds. The garden has an empty bed, where, statistically, you would expect more plants. Around Earth itself, layers of protection stack up like carefully placed hedges. The planet's molten core generates a magnetic field that wraps around it, deflecting much of the charged particle wind streaming from the sunday. Without this invisible shield, the atmosphere could have been eroded far more aggressively, and radiation at the surface would be harsher. Above the air, a layer of ozone absorbs most of the sun's ultraviolet light, that sharp, DNA-breaking radiation. Beyond the atmosphere, tens of millions of kilometers away, the orbits of Jupiter and Saturn sweep through space, capturing or deflecting a share of incoming comets and asteroids. Not all, not enough to guarantee safety, just enough to tilt the odds. Some comets are thrown outward into distant reservoirs. Some asteroids are nudged into more stable belts instead of being sent straight inward. Again, no wall is perfect, but the presence of these giant planets in these particular orbits changes the kind of sky Earth looks up into. It alters how often the story of life is interrupted by falling stone. Of course, the garden was not always quiet. In its early history, the inner solar system endured an era of intense bombardment. For hundreds of millions of years, roughly in the range of a little more than 4 billion to not quite 4 billion years ago, objects left over from planet formation rained down onto the young worlds. The evidence is still written on the Moon's face, in overlapping craters and ancient basins. This period, often called the Late Heavy Bombardment, was a time when oceans, if they existed, may have been boiled away repeatedly, atmospheres stripped and then slowly rebuilt. Then, somewhat abruptly in geological terms, that storm eased. The rate of catastrophic impacts dropped. There were still collisions, still local disasters, but the era of frequent world resetting blows ended. It is as though some reservoir of debris was finally depleted or rearranged, and the gate of the garden was quietly closed. From that point forward, life on Earth could grow within a landscape that, while dangerous, was not being erased over and over. In the middle of this violent youth, something happened that reshaped Earth in a way that seems almost theatrical. A body roughly the size of Mars, often referred to as Theia, is thought to have collided with the early Earth. The impact was so energetic that a large portion of Earth's outer layers and much of Theia itself were vaporized and thrown into orbit. From that halo of molten rock and metal, debris slowly clumped together and formed the Moon. This event was a catastrophe. It may also have been a reset. The newly formed Moon, relatively large compared with its planet, began to gravitationally lock Earth's rotation and stabilize its axial tilt. With the Moon's constant tug, Earth's axis does not wander wildly over time. Its tilt shifts, but within a band that allows seasons to be strong enough to stir climate, yet not so extreme as to freeze and fry whole continents in repeating cycles. The tides raised by the Moon pull on the oceans, shorelines, and even the crust, mixing heat and chemistry in ways that may have mattered deeply for the early evolution of life. The strike that could have destroyed everything, instead, carved out a companion that quietly steadies the planet. If you look at the sky on a clear night and see the Moon hanging there, you are seeing the frozen spray of that ancient collision. The calm silver disk is, in a sense, a scar that became a tool. Tilt and spin govern much of what you experience as weather and climate. Earth's axis is tilted by about a little more than 23 degrees relative to the plane of its orbit. It rotates once roughly every 24 hours. Change those numbers, and the character of the world shifts. A much larger tilt could make one hemisphere lean hard toward the sun for long stretches, baking summers and freezing winters into extremes. A much smaller tilt could flatten the seasons, leaving vast regions in a kind of uniform, unchanging climate. A much slower rotation would stretch the day, giving one side of the planet long periods of sunlight and long periods of darkness, deepening temperature differences between day and night. Instead, Earth sits in a middle ground. Days and nights come and go quickly enough that surfaces do not have time to swing to extremes. Seasons move slowly but not brutally. The details vary with ice ages and orbital cycles, with volcanic outbursts and greenhouse gases. But the basic rhythm remains: light and dark, warm and cold, wet and dry. Like the length of a song that happens to match a certain heartbeat, these periods align with the ways life has learned to adapt, migrate, grow, and rest. When you put all of this together, it becomes harder to see the solar system as just a random assortment of rocks. Moderate star. Long-lived. A habitable zone that Earth happens to occupy. A moon that steadies the tilt. Giant planets in positions that both menace and protect. A long quiet after an early storm. Nearly circular orbits. No close-in super-Earths. Empty space where other systems so often have planets. Is this simply what you get when physics is given enough time and matter to play with? Are these apparent coincidences just the natural outcome of many rolls of a cosmic dice, noticed only because you are one of the rare outcomes that can look back and count them? If someone wanted a planet where oceans could persist, where chemistry could grow slowly more complex, where fragile minds could eventually ask these questions, would they arrange things very differently from what we see here? Or are you reading meaning into patterns that do not have any? The way the human brain has always seen shapes in clouds and faces in wood grain. The solar system might be perfectly ordinary, and the feeling that it is slightly too reasonable might live entirely in you. For now, the suspicion just hangs there, like a question mark at the edge of the sky. To understand whether this garden is truly unusual, you have to compare it to others. And only very recently have we learned how to lean over the fence and look. So when the suspicion grew too strong to ignore, we did the only honest thing we could do. We started looking over the fence. The first real glimpse did not come from a gentle, sun-like system at all. It came from a dead star. In the early 1990s, astronomers studying a rapidly spinning neutron star, a pulsar named PSRB 1257+12, noticed that its pulses arrived with a strange, repeating irregularity. A pulsar is the dense, collapsed core left behind after a massive star explodes as a supernova. a city-sized sphere of matter spinning many times each second, sweeping beams of radio waves past us like a cosmic lighthouse. Those pulses are astonishingly regular. When their timing shifts, something is pulling. By carefully measuring those tiny variations, two astronomers, Alexander Wolszczan and Dale Frail, realized that the pulsar was wobbling, and the simplest explanation for that wobble was that unseen companions were tugging on it, planets. Not around a warm, life-giving star, but orbiting the ember of a star that had already died. When they announced their result, in the year 1992, it was a quiet revolution. These were the first confirmed planets found around a star other than the Sunday, but they circled a place where any garden would have long since burned. The supernova that created the neutron star would have blasted any earlier worlds, boiled away atmospheres, melted crusts, and drenched everything in radiation. If new planets formed afterward, they did so from wreckage. It was a scorched yard, a dead garden. Yet it carried a simple message. Planets, as a phenomenon. Still, there was a feeling of distance. Pulsars are exotic. No one expected such a system to resemble our own. The real shock, the one that bent the field's intuition, came a few years later, when astronomers turned their instruments toward a star more like our Sunday. On October 6, 1995, two Swiss astronomers, Michel Mayor and Didier Queloz, announced that they had found a planet orbiting the star 51 Pegasi, a sun-like star in the constellation Pegasus. The planet, which came to be called 51 Pegasi b, was a gas giant roughly comparable in mass to Jupiter, but it circled its star in only about 4 Earth days. To put that in words that land, a world larger than Earth by many times, made mostly of hydrogen and helium, orbiting so close to its star that its year is shorter than a human workweek. Its atmosphere is heated to temperatures where metals can vaporize. It is a hot Jupiter, a giant planet parked almost right against the stellar surface by solar system standards. For generations, our models of planet formation were built around the only example we had, our own system. Gas giants, in that picture, form far from their stars, in the cold outer reaches of disks, where ices can condense and solid cores can grow. The closer-in region is left to rocky planets, smaller, denser, like Mercury, Venus, Earth, and Mars. A Jupiter parked deep in the inner system felt almost illegal, yet there it was. The detection was not a fluke or a calibration error. The signal was clear, repeated, undeniable. A massive planet was whipping around 51 Pegasi in a tight, blistered orbit. The idea that our layout was the default suddenly became very hard to defend. What made that discovery possible was not a photograph of the planet itself, but the star's motion. When a planet orbits a star, both of them actually revolve around their common center of mass. The star does not sit perfectly still. It executes a small, repeated wobble. As it moves toward us and away from us along our line of sight, the color of its light shifts very slightly, toward the blue when it approaches, toward the red when it recedes. This effect, the Doppler shift, is the same principle that changes the pitch of a passing siren. By splitting starlight into a spectrum and measuring these shifts with exquisite precision, astronomers can infer the presence of orbiting planets. This radial velocity method does not show you the planet. It lets you listen for the star's subtle change of tone. Massive planets close into the star produce the strongest, fastest wobbles. They were the first to stand out in the data, like large dancers tugging obviously on their partners. Once you know to look, the sky changes. More stars were surveyed, more wobbles appeared. Hot Jupiters and other close-in giants began to populate catalogs. Each one was a reminder that other planetary systems could be radically different from our own tidy sequence of rocks and distant giants. Then came a mission designed not just to find a few odd cases, but to turn the question into statistics. On March 7, 2009, NASA launched a spacecraft named Kepler. Instead of moving from star to star, Kepler was built to stare almost unblinkingly at a single patch of sky, a tiny fraction of the whole celestial sphere, about 1/400th of the full dome. Within that patch, lay about 150,000 stars. Kepler's task was simple and patient: measure their brightness, again and again, for years. The method this time was different. If a planet passes directly between its star and our line of sight, it blocks a tiny portion of the starlight, causing a small dip in brightness. That dip repeats every time the planet completes an orbit and transits the stellar disk. By recording these dips, astronomers can infer the presence of planets, their orbital periods, and approximate sizes. Imagine watching a distant house with a single window lit. Every once in a while, someone walks in front of the lamp, and the light dims very slightly for a moment. You cannot see the person. You can only see the change in light. But if the pattern repeats steadily, you begin to guess their pace, their size, their path. That is the transit method. Kepler turned the sky into a sea of tiny, monitored windows. At first, the detections were rare, like whispers. A dip here, a hint there. Then, as years of data accumulated and new analysis techniques were developed, the catalogue swelled. Planets multiplied. Some stars hosted one. Others hosted several. Some systems showed chains of recurring dips corresponding to several worlds. A whole family moving in rhythm. Within a few years, the number of confirmed exoplanets grew from a handful to the thousands. For every confirmed world, there were many more strong candidates. From these samples, astronomers could estimate that the Milky Way alone might host tens of billions of Earth-sized planets in or near the habitable zones of stars, and even more planets of other types. In other words, planetary systems are likely the rule, not the exception. The galaxy is not a sparse scattering of isolated gardens. It is an overwhelming proliferation, but as the list grew, another, more subtle realization crept in. These gardens did not look like ours. Again and again, Kepler revealed systems where several planets of similar size orbited close to their star, packed into tight inner regions. Many of these planets were between Earth and Neptune in size, those super-Earths and mini-Neptunes that our own system lacks. Their orbits were short. Their years were measured in days or weeks, rather than in Earth's long journey around the Sunday. In some systems, the planets seemed to follow a kind of peas in a pod pattern, with radii and masses not identical but remarkably similar from one planet to the next. Imagine opening a set of drawers in different houses and finding that, in many of them, the socks are all neatly arranged in pairs of almost the same size and color. Then you look back at your own drawer and see 4 mismatched socks and a large winter coat. That was the feeling. Other planetary systems seemed to favor compact, uniform arrangements. Ours did not. One of the most striking examples came from a small, cool star with an unassuming name, TRAPPIST-1. In the second half of the decade of the 2010, a team announced that this ultra-cool dwarf star, much smaller and dimmer than the Sun, hosted a remarkable chain of planets. 7 worlds, all roughly Earth-sized, orbit the star in very close, resonant orbits. Several lie in the zone where liquid water could, at least in principle, exist on their surfaces. In physical distance, all 7 of those planets would fit well inside the orbit of Mercury. They are squeezed close to their star, huddled like beads on a short necklace. Their years range from a few days to a few weeks. Their gravitational interactions lock them into a sort of orbital harmony, where the timing of their transits reveals them tugging on each other, like musical notes forming chords. This is a garden, but not like ours. It is a cluster of Earth-sized worlds around a faint red star, crowded into a region where, if you stood on one planet's surface and looked up, the neighboring planet might appear several times larger than our moon does in Earth's sky. The idea of one habitable zone planet, plus distant giants, feels almost lonely when you place it alongside such tight, intricate families. As the catalogues broadened, the pattern repeated. Systems such as Kepler-11, with multiple low-density planets all orbiting closer to their star than Mercury is to the Sunday. Systems like Kepler-20, where Earth-sized and larger planets are interleaved in close orbits. Each discovery added another variation on a theme. Many planetary systems prefer to gather their worlds into compact inner arrangements. This raised an unsettling possibility. Maybe the solar system is not the template. Maybe it is the outlier. Of course, the data we gather are not neutral. The methods we use are biased. The radial velocity technique is best at spotting large planets close to their stars because they induce the strongest wobbles. The transit method is most sensitive to planets with short periods, which transit frequently, and which block a noticeable fraction of starlight when they pass. We are, in a sense, standing near a fence that lets us easily see the tall shrubs planted right up against the neighbor's house. The distant trees and the small flowers farther out remain hard to discern. It is possible that many systems like ours exist, with small inner rocky planets, an asteroid belt, and outer gas giants on long, cold orbits, but that we have not yet had the time or the tools to count them. It takes many years of observation to see repeated transits of a Jupiter-like planet, whose orbital period is measured in more than a decade. Many of the missions that have flown so far simply have not looked at any one star for long enough. Still, even after accounting for these biases, hints remain that certain features of our system are not typical. The sheer abundance of close-in super-Earths in the Kepler sample is hard to ignore. The absence of such planets here remains a silent, nagging question. Formation models, which attempt to grow planetary systems in computer simulations based on the physics of disks and gravity, tend to produce chains of planets that fill available regions unless something disrupts them. So astronomers are left with a tension. On one hand, they know their surveys are incomplete and their instruments are selective. On the other hand, even through that fog, some outlines are becoming clearer. Many stars are encircled by compact systems very unlike the wide, two-tiered architecture of our solar system. In some of those systems, orbital resonances, tidal heating, and intense stellar activity create environments that are challenging for the kind of long-term surface stability Earth has enjoyed. Disagreements emerge. Some researchers argue that once you correct for all the biases and allow for things we have not yet detected, the solar system may simply be one common outcome among many. Others contend that certain aspects, like the lack of super-Earths and the specific placement of Jupiter, do look statistically unusual. The arguments are technical. They revolve around distributions and models, around how many planets should form in certain regions of disks, how likely migration is to occur, how often it is halted. Beneath the equations, though, is a simple, human question that does not fit neatly in a paper's conclusion section. When you walk through this new neighborhood of planetary gardens, why does home feel so different? You can tell the story in purely physical terms. Disks of gas and dust around young stars form planets. Different initial masses, different temperature profiles, different histories of turbulence and magnetic fields produce different outcomes. Some systems remain compact and crowded. Others see their giant planets migrate inward and then outward, scattering material along the way. Some are shaped by close stellar encounters. Some are quiet. You can also, if you are not careful, slip into another language. You look at systems that seem naturally predisposed to pack planets close to their stars, and you look at ours, with its conspicuous gap and its distant guardians, and you start to talk about pruning, as if, in some invisible past, something walked through the inner solar system. Kicked out would be super-Earths, scrubbed the pathways, and left behind a leaner arrangement. No one can point to a photograph of such an event. There is no signature that reads clearly, "Here the gardener stepped." But as hot Jupiters and compact chains accumulate in catalogues, and as systems like TRAPPIST-1 remind us how different planetary families can be, the metaphor becomes hard to banish entirely. If the universe grows many styles of garden, and if, in the decades to come, it turns out that our tidy, stretched pattern is uncommon, then we face a choice in how we name that strangeness. We can call it coincidence, stacked upon coincidence, filtered through our own survival. We can call it the inevitable result of laws we have not fully worked out yet. Or, quietly, privately, some people will call it evidence of something that once reached in and rearranged things. For now, We do not have to decide. It is enough to notice that when we peek over the fence at other planetary yards, we do not see mirror images of our own. We see wildness, crowding, extremes, and surprising harmonies. We see variety far beyond what our textbooks once imagined. And somewhere in that variety, either our pattern will repeat again and again, or it will remain rare. The answer to which of those is true is hidden. For the moment, in data still being gathered, in surveys still being planned, in missions not yet launched, the sky is full of gardens. We have only just begun walking the neighborhood. The longer you walk the street and glance into other yards, the more your own front door begins to feel slightly out of place. Not worse, not better. Just tuned to a different pattern. As the Kepler data and later surveys were sifted and resifted, one recurring theme began to stand out. Many planetary systems did not just host planets. They hosted planets that were remarkably similar to one another, in radius, in mass, in spacing. Astronomers started calling this the peas in a pod pattern, because inside a single system, the planets often looked like members of a family, not a random collection of distant cousins. You can picture it. Take a star, draw a series of orbits around it. In a surprisingly large number of systems, you can populate several of those orbits with planets that are, within a small factor, similar in size. Not identical, but if you could scoop them up and line them against a wall for a height chart, you would see a neat cluster. Not a tiny child next to a giant, but a row of siblings. Even their spacing often follows a quiet rhythm. The orbital distances increase in a way that suggests a kind of geometric stepping, each planet somewhat farther out than the last, but not wildly so. In some systems, like an architectural designer with a fondness for symmetry, nature seems to have placed worlds at intervals that feel almost musical. When you place those systems next to ours, the contrast catches at you. Mercury, small and dense, racing close to the Sunday Venus, almost Earth's twin in size but hellish in conditions. Earth, blue and inhabited. Mars, half the diameter of Earth, thin air, cold deserts. Then suddenly a jump outward to Jupiter, the first giant, many times broader than Earth, followed by Saturn, Uranus, Neptune. The sequence goes small, somewhat bigger, similar, much smaller, then enormous. It is not a row of peas. It is a handful of different seeds. In the current exoplanet catalogues, the classic rocky inner planets, wide gap, distant gas giants, layout does not jump out as the dominant design. That does not mean it is not there at all. It means that, among the systems we can see well enough to characterize, many do something else. They pack several planets into the region close to the star. They fill in what, in our own system, is notably empty. One of the more unsettling styles are the hot Jupiter systems. These are not rare curiosities. They are a recognized class. A star, often similar in mass to the Sunday, a giant planet, as massive as Jupiter or even more so, parked at a distance so close that its orbit takes only a few days to complete. Its atmosphere puffs and roils under the star's intense heat. Its clouds, if you could call them that, might be made of silicate particles or even metals, condensing and evaporating in the furnace. In the house and garden metaphor, this is like planting a massive tree right up against the kitchen window. Its roots threaten the foundation, its branches block the light. Its presence dominates everything in the inner yard. For any smaller planets that may once have formed closer in, the inward migration of a giant like that could have been catastrophic, scattering them, throwing them into the star, or ejecting them entirely. There are also systems where no single giant dominates, but where chains of super-Earths or mini-Neptunes sit in compact, orderly rows close to the star. These are worlds with masses a few times that of Earth, up to perhaps 10 times, and radii that can be somewhere between Earth and Neptune. Many may be water-rich, some may have thick hydrogen-helium envelopes, some might be rocky with dense atmospheres. In these systems, 2 or 3 or more such planets orbit within distances smaller than that between the Sun and Mercury. Their years are measured in an Earth month or less. If you tried to overlay their architecture onto our own, those planets would all fit deep inside Earth's orbit, clustered in a region where, in our case, there is only one major planet and some minor rubble. Our solar system simply leaves that entire bed empty. No hot Neptune, no super-Earth, no planet. That is a middle step between Earth and the gas giants. For now, we can say that in the exoplanet data, such worlds are not exotic. They are common. The emptiness here is what raises eyebrows. Concrete examples help the strangeness land. Kepler 11 is a sun-like star hosting at least 6 known planets, 5 of which all orbit closer than the distance between the Sun and Mercury. They are all larger than Earth in radius, but smaller than Neptune. Puffed, low-density worlds packed into a tight formation. Their orbital periods range from fewer than 10 to around 50 Earth days. If you were living on one of those planets, your night sky would hold neighboring planets that loom bright, frequently transiting the star from your perspective. Kepler 20 offers another portrait. It hosts a mix of Earth-sized worlds and a pair of larger Mini-Neptunes, all inside the orbital distance of Mercury. The planets weave in an alternating sequence of smaller and larger, like beads of 2 different sizes strung on the same short cord. When you read through catalog descriptions of these systems, a phrase begins to recur. Compact multi-planet system. Compact multi-planet. Systems where most of the planetary real estate is used up close in, rather than stretched out. Why would nature favor such arrangements? One answer comes from simulations of planet formation in protoplanetary disks. When a star is young, it is surrounded by a disk of gas and dust. In that disk, solid particles collide, stick together, and grow into larger bodies. Over time, some of these grow into planetary cores. The cores interact with the gas and with each other. They migrate inward or outward. They may become locked into resonant orbits, where their periods are simple ratios of one another. In many computer models, when you let the physics run without artificially constraining it to reproduce the solar system, the natural outcome looks more like these compact chains than like our own sparse spread. Cores form in the outer disk, migrate inward as gas flows, pile up near the star, and in some cases stall in the inner region, forming multiple planets close in. Only under certain conditions do planets remain farther out in stable orbits like Jupiter and Saturn. In that sense, the P's in a pod systems might represent the default, the thing that happens unless something intervenes. Our system might then be the result of extra steps, extra accidents, extra violence. Perhaps our giant planets migrated inward for a while and then turned back. Perhaps their interactions with the disk carved out regions and prevented the formation of super-Earths. Perhaps the disk itself was lower in mass in the inner regions. If you follow this line of thought, the question shifts. It is no longer, how did the universe manage to create such strange systems? It becomes, what had to happen so that ours ended up looking so comparatively plain? There is a deeper psychological twist here. We are used to thinking of order as the default state and chaos as the departure. A tidy room is normal. A messy one is a deviation from that norm. A straight row of books is the baseline. A pile on the floor is the exception. But in physics, and especially in complex systems, the opposite often holds. Left entirely to themselves, systems explore many configurations. They flock, they scatter, they clump, they break. Variety appears naturally. Strict, long-term order usually requires constraints, rules, boundaries. The exoplanet data hints that planetary systems are similar. The natural thing might be a wild variety of architectures, some compact, some stretched, some with hot Jupiters, some with no giants at all, some with chains of super-Earths. When you look at a scatter plot of planetary radii versus orbital periods, the dots do not gather neatly along a single line. They form clusters, gaps, ridges, deserts, Against that backdrop, our solar system's comparatively smooth curve of planet sizes versus distance, its lack of very close-in worlds, its long, mostly empty stretch between Mars and Jupiter might be the actual anomaly. The tidy garden is the surprising one. The messy yards are simply what happens when you toss seeds into the wind and let gravity and time do their work. This is where the notion of a gardener, as a metaphor, grows more tempting. Not because there is necessarily a conscious hand, but because some combination of physical processes appears to have pruned, rearranged, and edited the young solar system in ways that many other systems did not experience or did not experience in the same sequence. Migration, for example, is not inherently gentle. A giant planet moving inward through a disk is like a snowplow moving through a street. It scatters material. It carves gaps. It can fling smaller bodies into the star or out of the system entirely. If, at some early time, Jupiter and Saturn moved inward and then reversed course, the wake of that journey could explain both our empty inner super-Earth region and the chaotic population of the asteroid belt. Collisions between embryos of planets can also radically reshape a system. The giant impact that created our moon is just one. There may have been many such events among forming bodies that no longer exist. In other systems, perhaps those events led to the merging of cores into larger super-Earths. Here, perhaps, they led to ejections, to breakups, to a thinning out rather than a build-up. Even the broader galactic environment plays a role. A close passage by another star during the formative years of a planetary system can disturb orbits, change inclinations, perturb outer belts. If the solar system happened to grow up in a pocket of space where such encounters were rare or absent at critical times, its disk may have evolved more gently, leaving room for a particular architecture to emerge. In denser stellar neighborhoods, more frequent flybys might have jostled things into more chaotic or more tightly packed configurations. When all of these ingredients are thrown together, you get the sense of a complicated recipe. Disks of different masses and temperatures, stars of different types and activity levels, migration histories that vary depending on timing, random collisions, external gravitational nudges. Out of this comes the diversity we see. So what, specifically, makes our garden look off compared to many of the ones we have glimpsed so far? There is the absence of close-in super-Earths. There is the presence of a large gas giant, Jupiter, at a distance that is neither very close to the Sun nor very far, roughly 5 astronomical units out, deep in the cold zone but not in the outermost dark. There is Saturn, farther out still, in a position where its gravitational dance with Jupiter can shape the asteroid belt and influence the stability of the inner planets. There is the relative lack of very eccentric orbits among the big planets. There is the fact that the total mass of solids in the inner solar system is surprisingly low compared with what some disk models might predict. If many systems begin with disks that would naturally form super-Earths, then perhaps something here prevented that. Perhaps Jupiter's early movement through the disk cleared out material that would otherwise have built such planets, leaving only enough to form small, rocky worlds. Perhaps resonances between Jupiter and Saturn stirred the asteroid belt and prevented it from coalescing into a planet. Perhaps subtle details in the disk's viscosity and temperature profile nudged growth along a different path. At some point, the language you use starts to matter. You can say, our initial conditions and dynamical history were such that the outcome falls in a lower probability tail of the distribution of possible planetary architectures. Or you can say, more simply, something walked through the young garden, stamped down some seedlings, and moved a few pots. Both descriptions try to capture the same basic idea. One hides the feeling behind equations. The other acknowledges it openly. Neither claims a literal gardener. Both leave room for one, if you are inclined. But neither requires that belief. What they do, together, is highlight how easy it might have been for our solar system to end up looking more like many of the ones Kepler has shown us. Packed inner planets, hot or warm Neptunes, perhaps even a hot Jupiter choking the inner yard. Instead, we have this stretched, layered, relatively spacious arrangement. When you internalize that, the question, why does our solar system look so rare, shifts tone. It is no longer abstract. It becomes as intimate as waking up and realizing that the street you live on is filled mostly with houses that are very different from your own. Some are crowded and noisy. Some are shaded by enormous trees that scrape the roof. Some are surrounded by tangled vines and wildflowers. Yours, by contrast, has a long, open front lawn and a line of distant, well-spaced trees. You can tell yourself this is just how the blueprints happened to unfold. You can tell yourself there were reasons in the building code, and that if you looked closely enough, you would find the clauses. You can also, if you stand in the doorway at night and look up, feel something like a presence in the absence, as if traces of decisions remain in the layout, even if the decision maker is only gravity and time. Among all the mechanisms that could have reshaped a young system away from the compact, peas in a pod default, one stands above the rest in our story. It is massive. It is distant. It carries most of the planetary mass in our system, and its gravity reaches across the garden, stirring belts, shielding, and threatening in equal measure. Jupiter. For a long time, it was easy to think of Jupiter as just another bright point in the sky, with a name from an old story. But once you see the layout of the garden, it becomes hard not to notice the enormous figure standing at the far edge of the lawn. Jupiter is not simply one more planet in the line. In terms of mass, it dominates the entire family. If you gathered all the planets together, every rocky world and every ice giant, and weighed them, Jupiter would outweigh the rest by a comfortable margin. It holds the bulk of the planetary mass that orbits the Sun, other than the Sun itself. Its gravity reaches inward and outward, tugging at asteroids, reshaping comet paths, tugging subtly on Saturn, stirring the Kuiper belt and the distant Oort cloud. It is less a lone tree and more the central hinge of a gate. Because of that, its influence is everywhere, even if you do not feel it directly as you stand on Earth. The main asteroid belt, lying between Mars and Jupiter, is carved with gaps where Jupiter's orbital resonances pump up the eccentricities of rocks and clear out regions. Some asteroids are shepherded into stable bands. Others are nudged onto new paths, sometimes inward, sometimes outward. Over billions of years, Jupiter's constant pull has been like a slow hand running through gravel, sifting, arranging, ejecting. This is where the idea of Jupiter as a kind of protector enters the conversation. In many simulations of the solar system's evolution, the presence of a massive planet at Jupiter's distance does reduce the number of long-period comets and large bodies that plunge into the inner region. Some objects that might otherwise wander into Earth-crossing orbits are intercepted, captured as moons, diverted into safer orbits, or flung away entirely into interstellar space. In that story, Jupiter is a tall hedge on the outer boundary, breaking the worst of the incoming stone wind. It is a comforting picture. A benevolent giant, standing watch, taking the hits so that the smaller, fragile worlds behind it have a chance to remain. And there is some truth in it. There are families of comets, like the Jupiter family comets, whose orbits are clearly molded by its gravity. There are impact rates that change when you remove Jupiter from the equations. When you ask, in a model, what if this planet were not here? The sky over Earth often becomes more dangerous, but the reality is more complicated, and that complication makes the metaphor richer rather than weaker. Jupiter can also send bodies inward. A comet that passes close can be slingshotted onto a path that crosses Earth's orbit. An asteroid nudged into a resonance can have its orbit stretched until it intersects the inner planets. The same gravitational reach that sometimes shields also sometimes aims. The hedge can deflect a stone away from the house or, with slightly different timing, help it find the window. So, Jupiter is not purely a guardian. It is a gatekeeper. It regulates traffic through the system, not always in our favor. It is a double-edged tool. To understand why it might have been essential in shaping the whole architecture of the solar system, not just the rate of individual impacts, you have to go back to its youth. One influential idea in planetary science, developed over the past few decades, is called the Grand Tack hypothesis. The name comes from sailing. To tack is to change direction in the wind. In this picture, Jupiter did not simply form where we see it now and remain in place. It migrated. Early on, when the solar system was still filled with gas, Jupiter formed in the outer disk and then began to move inward, spiraling slowly toward the Sunday. As it moved, its gravity disturbed the planetesimals and embryos in its path. Cores that might have grown into super-Earths were scattered. Material was shepherded into resonant bands, some of it accreted, some of it ejected. The asteroid belt region was stirred violently. This inward voyage might have continued until Jupiter reached a distance comparable to where Mars now orbits, or even closer. Then, in this hypothesis, Saturn formed and also began to migrate inward. The two giants became locked in an orbital resonance with one another. Their gravitational dance changed the way they exchanged momentum with the gas disk. Instead of continuing deeper inward, the pair reversed course and moved outward again, retreating to the positions we see today. Jupiter tacked like a boat turning its bow and heading back out toward deeper water. If something like this really happened, it would have enormous consequences for the inner solar system. Jupiter's inward pass would have depleted the material available to grow large, rocky planets. Its outward retreat would have left behind a region that had been churned and thinned. The inner planets that eventually formed in that space would be smaller than they might otherwise have been. Mars's unusually small size, compared with Earth and Venus, might be a fossil of this depletion. The mixed composition of the asteroid belt, with some objects showing signatures of formation in warmer inner regions and others in colder outer zones, might be another fingerprint. Numerical simulations of disks with migrating giants show that such in and out movements can indeed produce inner systems with low mass and an asteroid belt like ours. They can reproduce certain features of the mass distribution, certain gaps, certain resonant structures. No model is perfect. They depend on parameters we cannot observe directly. But the broad picture is that a Jupiter that did not stay put, but instead swept through the young garden could, in principle, explain much of what we see. It is hard not to picture a gardener with a rake walking down a newly planted bed, tearing up sprouts that grew too close together, then stepping back and letting the survivors establish themselves in the cleared soil. Jupiter's journey, in that sense, would have been a kind of churn and retreat move, not gentle, not precise, but enough to leave behind a zone that was poorer in raw material and richer in long-term stability. After the gas disk dissipated, Jupiter's role did not end. Its gravity continued to shape the Kuiper belt and the scattered disk, the distant reservoirs of icy bodies. Interactions between Jupiter, Saturn, Uranus, and Neptune can explain, in some models, a later rearrangement of orbits that may have kicked off the late heavy bombardment. Again, the picture is of a system that did not gently glide into its current configuration, but one that jolted, shuffled, and then settled. From a scientific standpoint, there is an ongoing debate about how exactly to interpret Jupiter's role. Some studies emphasize its protective influence, showing reduced impact rates on an Earth-like planet when a Jupiter-like mass is present at roughly Jupiter's orbit, compared to cases with no giant or with a giant in a very different place. Other work highlights its capacity to scatter hazardous objects inward as well as outward, showing that under certain conditions, a giant planet can increase the flux of potential impactors. Is Jupiter a brake or a wrecking ball? The answer seems to be, it is both. It is a moderator of chaos, not an eraser of it. It shapes the statistics of what falls inward, the timing and size of events, rather than simply turning them off. This duality is what makes Jupiter so interesting in the gardener metaphor. A pruning tool can remove diseased branches and allow new growth. It can also, if used with too much force or in the wrong season, damage the tree. The same shears both protect and threaten. It is the way they are used, and where and when, that matters. If you try a thought experiment and imagine removing Jupiter entirely from the solar system, the stakes become clearer. Picture a young solar system in which a star like the Sun forms. Rocky planets grow in the inner disk, and smaller icy bodies form farther out. But now, instead of a great giant planet forming at a few times the Earth-Sun distance, the outer regions remain populated only by smaller bodies and perhaps some modest ice giants. There is no single mass to dominate the outer gravitational landscape. In computer models of such a system, the rate at which comets and asteroids wander into the inner region can rise. Without a massive planet to either clear them out efficiently or lock them into certain stable resonances, more objects maintain long-lived, chaotic orbits that occasionally intersect those of the inner planets. Over hundreds of millions of years, the cumulative number of large impacts on an Earth-like world can increase, sometimes dramatically. Each such impact is a reset button. A sufficiently large collision can vaporize oceans, darken the sky with dust for years, collapse food chains, sterilize large parts of the biosphere. Life can, in principle, recover from even severe events. But recovery takes time. If resets happen too frequently, complex life may struggle to gain a foothold. Ecosystems may advance a certain distance and then be thrown back down the slope again and again. It is impossible to know exactly how many fewer or more impacts Earth has received because of Jupiter's presence. We have only one timeline, one planet, one record in the rocks. But the models suggest that a system without a Jupiter analog could be less forgiving, more prone to catastrophic interruptions. The garden would be stomped more often by falling stone, and the fragile, intricate flowers of complex organisms might not have as many unbroken seasons in which to bloom. But the picture is not simply that a big planet somewhere out there is good. Position matters. Mass matters. A much more massive Jupiter, closer in, could destabilize Earth's orbit through gravitational perturbations, slowly stretching our path into a more eccentric shape or tilting its plane. That, in turn, could send climates into harsher cycles. A much closer Jupiter could also disrupt the formation of Earth entirely, sweeping up too much of the inner disk's solid material, leaving only smaller remnants. Similarly, a Jupiter far farther out, or much less massive, might fail to provide whatever protective effect it currently offers, allowing more long-period comets to wander unperturbed into the inner region. Or it might fail to play the role it may have played in shaping the asteroid belt and the inner mass distribution in the way that produced our small rocky planets. In that delicate balance, Jupiter begins to look just right, in a way that is hard to ignore. Not perfect, not tuned to many decimal places, but roughly the right mass, in roughly the right place, to both sculpt the system and to avoid tearing it apart. A little heavier, a little lighter, a little closer, a little farther, and the history of Earth might have unfolded very differently, or not at all. If you lean into the gardener metaphor, you might say, if someone wanted to prune a young system into a long-term stable shape, they might place a giant planet at about this distance, with about this mass, to do the work. It would stir the outer debris, carve gaps, and moderate the flow of impactors, while still allowing a habitable zone planet to orbit closer in on a relatively stable, nearly circular path. No one is claiming that this is what happened. The data do not whisper secret intentions. They simply show that the presence of Jupiter has been central to the solar system's story. It is entirely possible that disks and gravity naturally produce such giants at such distances often enough, and that there is nothing more to say about it than that. It is also possible that the combination of factors that gave us this particular configuration is, in a statistical sense, unusual. When you stand outside on a clear night and see Jupiter shining as a bright, steady point, what you are seeing is not only a planet, you are seeing one of the main structural beams of the solar system. You are seeing a relic of the disk that once existed here, a survivor of migrations and interactions, a body whose gravity has been curating the distribution of other bodies for billions of years. It is a strange feeling to look up at a light in the sky and think not of mythic kings or thunder gods, but of impact rates and orbital resonances, of late heavy bombardments that did and did not happen, of continents that might never have formed, oceans that might never have stabilized, if that point of light had followed a different path. And because we are no longer alone in our knowledge of planetary systems, the question that naturally follows is one we can now imagine answering. Do other stars have their own Jupiters like this? Not just any giant planet, but a massive world on a wide, nearly circular orbit around a sun-like star, sitting beyond a region where small, rocky planets might live. If such arrangements turn out to be common, then Jupiter's story becomes less eerie. The Gardner tool is simply part of the standard kit that physics builds around many stars, and our sense of specialness shifts. Our garden is one of many carved by similar shears. If, however, careful surveys of other systems reveal that giants like Jupiter, at such distances, in such orbits, are rare, then the feeling of walking through a peculiar yard only deepens. It would mean that the particular way our garden was pruned is not the usual outcome. That this specific layout, with a tall hedge at just this distance and just this height, is an exception. Right now, the truth sits in data that are still being gathered and in analyses still being refined. Telescopes on Earth and in space are listening for wobbles, watching for shadows, measuring tiny motions. Somewhere in those patterns is a count, however imprecise, of how often the universe builds a system that looks, from a distance, like ours. Until that count is clear, Jupiter remains both what it has always been and something more in our imagination. A giant planet in the outer solar system, a mechanical hub of orbits, a potential shield and a potential threat, and, in the quiet hours of the night, a possible tool in the hands of a gardener we may never be sure exists. Once you start to suspect that a single giant can reshape a whole garden, a quieter thought follows behind it. If this worked here, has it worked elsewhere? And if so, where are those other yards that feel like home? To even ask that, you have to decide what home means in this context. Not in terms of air or oceans or cities, but in terms of architecture. In this story, a solar system twin is not just any system with a few planets. It is a particular pattern. Picture the requirements laid out gently on a table. First, a star broadly similar to the Sunday. Not identical in every detail, but close enough in mass and luminosity that its habitable zone sits at roughly the same kind of distance. Long-lived. Not wildly variable. Then, at least one rocky planet in that habitable zone. Big enough to hold an atmosphere for billions of years, but not so massive that it becomes a mini-Neptune shrouded in thick gas. And, farther out, a giant planet comparable in mass to Jupiter, orbiting on a wide, roughly circular path far beyond the habitable zone, where it can act as a gravitational moderator rather than a direct source of heat. Sun-like star, habitable rocky world, distant Jupiter. Those three together define the kind of system we are quietly searching for when we say, like ours. There are other details that might matter too, like the presence of additional giants, the exact eccentricities of orbits, the level of stellar activity. But as a first sketch, those three pieces are enough to ask a simple question. How many are there? At the moment, the honest answer is unsettling in its emptiness. Among the thousands of exoplanet systems we have detected, the number we can point to and say with confidence, this is a full solar system analog with all three of those ingredients confirmed, is essentially none. We know of sun-like stars with giant planets on wide orbits. We know of sun-like stars with small rocky planets in or near their habitable zones. But clean, fully mapped systems that show both a temperate rocky planet and a distant Jupiter around the same star remain, observationally, ghosts. That does not mean the galaxy is empty of them. It means we have not yet been able to see them clearly enough. Part of the problem lies in the way our tools work and in the way they are bound to time. Jupiter takes about 12 Earth years to complete one orbit around the Sunday. For a distant observer watching our star for changes, that means the periodic signals caused by Jupiter's pull are spread over more than a decade. You have to watch for a long time to recognize the pattern. Kepler, remarkable as it was, stared at its main patch of sky for about 4 continuous years. That is long enough to see many transits of a planet with a short year, A world orbiting in just a few days or weeks will cross its star dozens of times in that window. But a Jupiter-like planet, with a year measured in more than 10 Earth years, might not transit even once within Kepler's gaze. And even if it did, a single dip would not be enough to confirm a planet. You need repeats. You need patience that outlasts a single mission. The transit method is biased, by design, toward the inner parts of planetary systems. It is like watching the front porch and hallway of a house and trying to infer the existence of a backyard. You can, in principle, see a tall tree walk past the window if the timing is just right. But it is far easier to see the people moving around indoors. Radial velocity, the Doppler wobble method, fares better for long-period giants. The gravitational pull of a Jupiter analog on its star produces a slow, repeating change in the star's velocity along our line of sight. With sufficiently precise instruments and years of data, astronomers can detect those changes and infer the presence of the planet. Some of the first known Jupiter-like planets on wider orbits were found this way. But radial velocity surveys are not mass scouting machines. They require repeated, high-precision observations of individual stars over many years. That is time-intensive. You cannot easily apply that level of attention to hundreds of thousands of stars at once. Instead, you build up samples star by star, campaign by campaign, instrument by instrument. The resulting catalogue is rich, but patchy. So we find ourselves in an awkward position. The techniques that are best at surveying large numbers of stars are biased toward close-in planets. The techniques that can see the more distant giants are slower and narrower. Together, they give us fascinating glimpses, but they do not yet yield a clean census of systems that host both an Earth-like planet in the habitable zone and a Jupiter-like giant far out. Absence in the current data does not equal absence in reality. It may simply reflect where we have looked, how long we have watched, and what kinds of signals we are most sensitive to. Our tools have been fantastic at revealing hot Jupiters, warm Neptunes, and compact chains of super-Earths. They have been less fantastic at revealing stretched, layered systems like our own. It is a little like birdwatching in a dense forest with a pair of binoculars that can only focus on branches close to the trunk. You will quickly build a list of species that prefer to hop near the center of trees. You will be forgiven for thinking, for a while, that this is what birds are, and you will have almost no idea how many others glide quietly at the treetops or skim the water far beyond the reach of your glass. Yet, even after bending over backward to account for these biases, some hints remain that systems like ours may not be overwhelmingly common. Statistical studies that combine radial velocity data, transit detections, and models of planet populations suggest that Jupiter analogues around Sun-like stars exist, but perhaps in only a modest fraction of systems. Small, temperate, rocky planets around Sun-like stars also exist. But again, the exact statistics are still being refined. The product of those two probabilities matters. If only some Sun-like stars host distant Jupiters, and only some host habitable zone rocky planets, and those two sets only partially overlap, then the number of true solar system analogues could end up being a relatively small slice of the galactic population. Not vanishing, not unique, but not the default either. When you follow that line of reasoning, you begin to sense the weight of the implications pressing in at the edges. If this particular architecture, one moderate star, one long-lived habitable rocky planet, one outer giant gatekeeper is rare, and if that architecture is especially conducive to maintaining stable conditions for complex life over billions of years, then life like ours may be rarer still. Not life in general. Microbial life might thrive in many settings, beneath ice crusts, in subsurface oceans, in thick atmospheres, in environments we would find lethal. But minds that build radios and telescopes, that map star systems and ask statistical questions about their own rarity, those might require a quieter, longer stage. In that scenario, our solar system would be one of relatively few stages in the galaxy where the play of technological civilization manages to unfold. Not necessarily the only one, but one of a limited number. Each such stage would carry an enormous share of the universe's capacity to know itself. If you are inclined toward the gardener metaphor, you might say, if a gardener exists, they did not plant many of these particular beds. There is another possibility that is just as powerful and just as unresolved. The architecture we live in may in fact be fairly common in the galaxy. There may be many sun-like stars with habitable zone rocky planets and distant Jupiters. They may simply be hard to see with the tools and time baselines we have had so far. In that case, our failure to identify many full analogues yet is more about our ignorance than about true rarity. If that is how reality is, then the future is filled with a different kind of weight. It would mean that the Milky Way is dotted with gardens broadly similar to ours, each with its own story of impacts and climate swings and evolutionary experiments. The gardener, in that telling, is just physics, repeating a pattern that turns out to be efficient at producing long-lived stable zone. Our sense of loneliness might soften, not because we have found anyone yet, but because we would know, with numbers, that the stage on which beings like us can emerge is not a singular fluke. Both scenarios are unsettling in their own ways. Rare, and you inhabit a fragile exception. Common, and you are part of a vast, unseen community of similar structures, even if you never speak to any of them. In both cases, you lie awake under the same sky, on the same small world, around the same star. For now, what we have is something like an incomplete map. Transit surveys have filled in many dots close to stars, showing us where hot and warm planets reside, especially those that are large enough and near enough to cause noticeable dips. Radial velocity surveys have traced out some of the larger wobbles that hint at giants on wider orbits. Direct imaging has, in a few cases, captured actual photons from massive planets in very wide orbits, far from their stars. But the region of parameter space that specifically corresponds to Jupiter analogues around Sun-like stars, and the joint region where those coexist with small habitable zone planets, is still sparsely sampled. When you look at the map as a whole, it is as though someone has shaded in the inner districts of a city with fine detail, left the outer suburbs in faint outline, and erased the labels altogether in some neighborhoods. We know there are stars with planets. We know there are stars with giants. We know there are stars with small temperate worlds. What we lack, still, is a robust, statistically grounded count of systems that gather all three of those attributes. That missing piece is crucial. It does not just change a number in a paper. It changes how we feel when we say the word home. You can sense that absence when you listen to astronomers talk about the future. There is an awareness that a major ingredient is missing from our understanding, that we are, essentially, trying to estimate how unusual our garden is by squinting through a keyhole at very different yards and guessing about the ones we cannot yet see. So the field has quietly turned to a different kind of tool. Not a telescope that waits for shadows to cross a star. Not an instrument that listens for changes in a star's pitch along our line of sight. But something more like a ruler, held up to the sky with almost absurd precision, to measure the tiny, sideways motions of stars as their planets pull them gently to and fro. Astrometry, the art of charting positions and motions on the sky. In that realm, one mission stands out as the next possible Gardner detector, a spacecraft launched by the European Space Agency, placed in a quiet orbit around the Sun, scanning the sky over and over, recording the positions of roughly billions of stars with unprecedented accuracy. Watching, over years, as those positions trace tiny loops and curves, betraying the gravitational influence of unseen companions. Its name is Gaia. Gaia is not a telescope you visit. It is more like a quiet metronome in the dark, counting motions so small that no human eye would ever know they were there. From its orbit around the Sun, trailing Earth at a safe distance, Gaia spins and scans and spins again, sweeping its gaze across the sky over and over. Its job sounds simple when said in one breath. Measure the positions and motions of roughly 2 billion stars with such precision that the Milky Way stops being a flat picture and becomes a three-dimensional map. But what that really means is that Gaia is watching for the tiniest betrayals of straight lines. Every star in the sky is moving through space, drifting in its own orbit around the galaxy's center, Most of that motion, when projected on the sky, looks like a slow, nearly straight path. But if a star has a massive planet, or several, the star does not travel alone. Star and planet orbit a shared center of mass. The star, though so much heavier, is tugged into a small orbit of its own. To a distant observer, its path is not perfectly straight, but a gentle curve, a looping wobble. This is what astrometry measures. Not the brightness change when a planet crosses the star, not the color shift as the star moves toward and away from us, but the sideways dance, the tiny loops drawn on the celestial sphere. The power of astrometry lies in a simple geometric fact. The farther from the star a planet orbits, the larger the circle the star must trace around the center of mass. A distant giant planet can make its star's position wobble by a small but measurable amount. For a very close-in planet, the wobble is tiny. For one on a wide orbit, the lever arm is longer, the effect bigger. That makes astrometry almost the mirror image of the transit and radial velocity techniques. Transits and Doppler shifts are most sensitive to close-in planets. Astrometry becomes increasingly sensitive in the outer regions, precisely where Jupiter-like giants tend to live. In the area where our current map is faint, Gaia's vision is sharpest. Of course, the challenge is that, from our perspective, even these large stellar loops are microscopic. Gaia must be able to tell whether a star appears to move by an angle on the sky, equivalent to the width of a human hair seen from hundreds of kilometers away. To do that, it repeatedly measures the relative positions of stars as they drift across its detectors, building up a web of angular separations that can be solved, like a gigantic puzzle, for distances, motions, and wobbles. Early on, the first Gaia data releases focused on the big picture: distances to stars, their proper motions, their distribution in the Milky Way. But buried inside that wealth of information are the subtle signatures of planets. As analysis methods improved and time baselines lengthened, the mission began to reveal individual systems. Giant planets, such as Gaia 4b and Gaia 5b, detected through the small astrometric deflections they induce, serve as proof that the method works in practice, not just in simulations. These are worlds we do not see as points of light, but whose existence we infer because their stars do not travel perfectly straight. Each one is a reminder that Gaia is not just drawing a static map of where stars are, but recording the faint imprint of what orbits them. The real transformation, though, is expected to come as Gaia accumulates more and more years of data and releases refined catalogs. With each additional year, the loops traced by stars with long-period planets become more complete, and the confidence in those detections grows. A number of studies have tried to predict what Gaia will eventually reveal. Based on simulations of its sensitivity, one analysis suggests that by the time the mission's fourth major data release arrives, sometime around the middle of the decade of the 2020s, Gaia could detect on the order of about 7,500 exoplanets through astrometry alone. Many of those would be massive planets on orbits similar to or wider than that of Jupiter. That is already a wave compared with what we have now, but Gaia is expected to operate for longer than the duration required for that fourth release. With roughly 10.5 years of observations, a later fifth major data release, projected for the early years of the decade of the 2000s and 30s, could potentially include signals from around 120,000 planets. The exact numbers will depend on the mission's lifetime, the performance of its instruments, and the criteria used in analysis. Still, the order of magnitude is staggering. Imagine it. Not a few dozen outer giants, not a few hundred, but tens of thousands, maybe more than 100,000, each tugging on its star, each drawing a tiny invisible loop on the sky. Some will be lone sentinels. Some will be part of systems that also host inner planets known from transits or radial velocities. For the first time, we will be able to look at planetary architecture from the inside and the outside at once for a statistically significant number of systems. That is where Gaia's data meets the work of missions like Kepler and the Transiting Exoplanet Survey Satellite, often called TESS. Kepler has already provided us with detailed statistics on close-in planets around stars in its original field. TESS is now surveying nearly the whole sky, focusing on bright, nearby stars. Both missions excel at finding inner planets whose orbits take days to months. Gaia, by contrast, is built to reveal the presence of outer companions to those same stars, even when those companions never transit. When we combine these datasets, a new kind of map emerges. For some stars, we will know about small, possibly rocky worlds in close orbits from transit data, and also know about giant planets far out from Gaia's astrometric wobbles. In garden language, Kepler and Tess show us the arrangement of stones and shrubs near the front door. Gaia shows us the presence of large trees near the fence, even if we never see their branches cross the window. Put together, they allow us to sketch entire yards instead of isolated patches. If there is such a thing as a Gardner signature in planetary system design, a pattern in which habitable zone rocky planets are statistically more likely to be accompanied by distant giants of certain masses and at certain distances, Gaia is one of the best tools we have for finding it. Not because it was designed with that metaphor in mind, but because it targets exactly the mass and orbital regimes where such patterns would appear in the statistics. You can think of it as a kind of cosmic handwriting analysis. Each planetary system leaves a trace in its host star's motion. Some traces will be simple, the loop of a single giant. Some will be more complex, the superposition of several motions. When Gaia's data are fully explored, astronomers will be able to classify these patterns in bulk. How many stars, like the Sun, host a single Jupiter-like planet beyond the habitable zone? How many host multiple giants? How many show no sign of such companions at all? From there, the question that has been quietly humming in the background of this whole story can finally be given a number. Among stars like the Sun, how many have at least one small, temperate planet and at least one distant, Jupiter-like giant? Not one or two intriguing examples, but one in this many or one in that many." End quote. If it turns out that such systems are common, cropping up again and again in Gaia's harvest, then the cosmic gardener, as a metaphor, looks less like a singular artist and more like a set of rules. Physics itself would be the gardener, regularly shaping disks into similar forms. Our solar system would be one of many gardens pruned in comparable ways, its architecture a recurring theme in the Milky Way. If, on the other hand, Gaia's data reveal that Jupiter analogues around Sun-like stars are uncommon, and that their overlap with habitable zone rocky planets is even rarer, then the sense of living in a rare, suspiciously tidy garden deepens. Our system's layout would occupy the tail of some distribution of outcomes. Most stars would host different arrangements: compact chains, no giants, misaligned orbits, wandering super-Earths. The combination we depend on would be a minority taste of the galaxy. Neither outcome tells us whether life exists elsewhere. Neither tells us whether minds like ours are frequent or vanishingly sparse. But both outcomes change how we think about our own situation. Commonness shifts our questions from "How did this happen at all?" to "Why has this particular common pattern bloomed into consciousness here, now?" Rarity intensifies the feeling that we inhabit an exception that might not be repeated often. In a way, Gaia's real gift is not just the raw numbers it will deliver, but the way it connects the abstract geometry of stellar motions to the fragile realities of planets. Each tiny wobble it records is a fossil of gravitational companionship, a hint that somewhere around that star a world is tracing its orbit, unseen. It is strange to imagine that, right now, while you listen to this, Gaia's detectors are still gathering photons from distant stars. It spins, it scans, it notes that this star has shifted by an amount so small that, to your eye, it might as well not have moved at all. It does this again, and again, and again, year after year. On the ground, teams of scientists and engineers work with those measurements, correcting for subtle effects, building catalogs, comparing them, releasing them. Data releases feel, from the outside, like dry technical milestones. For the people waiting on the answers hiding inside, they are more like the slow development of a photograph in a dark room. At first, nothing. Then faint outlines. Then shapes. Then, one night, you realize there is a face looking back. In Gaia's case, what will be looking back at us are patterns of motion that speak of worlds. Some will be massive, cold giants. Some will be smaller. Some will be part of systems that, when combined with other observations, resemble ours. Some will be unlike anything we have imagined. The telescope itself does not care. It is an instrument, following its design. But we care. We are the ones who have given names to these patterns. Hot Jupiters, super-Earths, Mini-Neptunes, Jupiter analogues. We are the ones who stand in our own small garden and wonder whether there are others like it. When the full arc of Gaia's mission is complete, the sky will not look different to your naked eye. The constellations will be the same lines you have always drawn. Orion will still raise his arm. Cassiopeia will still recline on her throne of 5 bright stars. But behind those familiar stick figures, a new layer of understanding will exist. For many of the points of light, we will know, in a statistical, quiet way, whether they host giants like Jupiter, whether they host chains of inner planets, whether their architecture echoes ours or not. And somewhere in the enormous archive of tiny measured wobbles, written in numbers and coordinates, lies the answer to a question that no star ever needed to ask. How often does the universe build a garden like this one? You will not hear that answer shouted. It will arrive as a graph in a paper, a fraction with uncertainties, a plot showing one kind of system more frequent than another. But if you step away from the figures and close your eyes, you can translate it back into feeling. In the dark, Gaia's dataset is like a recording of stars breathing. Each little deviation, each small loop, is an inhalation, an exhalation, caused by unseen planets pulling on their suns. In that quiet, statistical music, the rarity or commonness of our own garden's tune is hidden. One day, someone will press play on that part of the song and tell us what they hear. Even the most delicate garden is shaped by the street it lives on. The same is true of stars, even if their streets are made of starlight and dark matter instead of pavement. If you could pull back far enough to see the Milky Way from the outside, you would see a barred spiral galaxy, a glowing disk with arms curling outward, a bright, crowded center, a dimmer, more tenuous edge. Stars are not scattered evenly through that disk. Some regions are dense, busy, loud. Others are sparse, thin, quiet. Astrobiologists sometimes talk about a galactic habitable zone, an idea that stretches the notion of just right beyond a single star. Near the galactic center, the density of stars is high. Supernovae, those powerful deaths of massive stars, are more frequent. Black holes and neutron stars churn. Radiation fields can be intense. Gravitational tides from passing stars are stronger, more common. It is a place rich in heavy elements, because generations of stars have lived and died there, seeding the gas with metals that help build rocky planets. But it is also a dangerous neighborhood for fragile atmospheres and long-term stability. Far out in the galaxy's outskirts, the opposite problem appears. Out there, the star density drops. Life is quieter. But so is the history of element production. There may be fewer heavy elements to work with. Gas clouds are more pristine, less enriched by previous generations. Forming small, rocky planets there might be harder, simply because the raw material for solid cores is scarcer. You can have peace, but not enough bricks to build with. Somewhere between those extremes lies a broad band that is neither too crowded nor too empty. Neither too blasted by radiation nor too starved of metals. It is not a sharply defined ring, and the concept is still debated. But as a rough picture, it suggests that there are regions of the galaxy where the conditions for forming Earth-like planets and keeping them stable for long spans of time might be more favorable. Our own star sits in that in-between space. The Sun lives in a smaller structure called the Orion Spur, a modest lane of stars between two of the Milky Way's major spiral arms. It is not in the blazing central bar, where distances between stars shrink, nor way out in the faint, thin edge of the disk. It is more like a suburb, neither downtown nor countryside. In that suburb, the average distance between stars is measured in light years. That is close in cosmic terms, but far enough that direct stellar encounters, the kind that seriously disturb planetary systems, are rare on human and even geological timescales. The sky is rich with stars, but not so full that their gravity constantly tugs on one another's outer clouds. That quietness matters. A star that spends its life in a crowded cluster, where close passes are more common, is more likely to have its outer belt stripped, its Oort cloud perturbed, its planetary system jostled. The inner orbits we call home could be tilted, stretched, or even unbound by a sufficiently close encounter. Our position in a less crowded region has likely reduced the number of such disruptions. The Sun does not sit still, of course. It orbits the center of the Milky Way, just like every other star in the disk. One full circuit, often called a galactic year, takes on the order of 225 to about 250 million Earth years. In the time since the first complex animals walked the ocean floor, the solar system has completed only a few of these great turns. Dinosaurs rose and fell within roughly a single galactic year. Mammals spread, humans appeared, cities rose, radio waves flickered into space. All of recorded human history fits into a sliver of one galactic year, like a few seconds in the arc of a long, slow day. As the Sun travels, it gently weaves above and below the galactic plane, moves slightly inward and outward, passes near different patches of interstellar gas and stars. Over billions of years, those changing surroundings could have affected the flux of comets, the level of cosmic rays at Earth, the rate of nearby supernovae. Yet through all of that, the solar system has remained intact. Its major planets are still on their nearly circular paths. Its inner garden is still here. The Milky Way itself is not a static backdrop. It has grown by merging with smaller galaxies, swallowing them, stretching their stars into long streams that wrap around the disk and halo. Astronomers can see these tidal streams in Gaia's data, faint rivers of stars that were once part of other systems. Some of the Sun's more distant neighbors may have been born in those captured galaxies, only later becoming residents of the same broad city as us. Through those mergers and rearrangements, the solar system was never torn apart. No passing giant galaxy ripped the Sun from its orbit, no catastrophic tidal force stripped away its planets. That, again, is partly timing and partly placement. The most violent phases of the Milky Way's assembly occurred early, before the Sun was born. By the time our star formed, around half the age of the universe ago, the galaxy had already done much of its rough construction. The neighborhood was still dynamic, but not in constant demolition. In the far future, the Milky Way's story will take another dramatic turn. The Andromeda galaxy, our nearest large neighbor, is slowly moving toward us. In about 4.5 billion years, the two spirals will begin a long, slow merger, passing through one another, their stars mostly missing in vast near collisions, their gas clouds compressing, igniting new bursts of star formation. Over perhaps several billion years, the graceful disk shapes will distort, intermingle, and eventually settle into a new, larger galaxy. For individual stars like the Sun, the chance of a direct collision with another star during this dance is very low, because the spaces between stars are so immense compared with their sizes. But the gravitational potential of the combined system will change. Orbits will slowly reshuffle. Some stars may be flung into long, looping paths far from the center. Others may sink inward. Whatever planetary systems still exist will ride those tides. The Sun may not be around to see the end of that drama. Its own natural evolution will likely turn it into a red giant, and then a white dwarf on a timescale similar to or shorter than the merger. Still, it is quietly sobering to imagine that even our galaxy's tranquil suburb is only temporarily so. The whole city is moving, colliding, remaking itself. If you find the gardener metaphor slipping back into your mind here, you are not alone. It is one thing to talk about the arranging of planets within a solar system. It is another to consider that the larger environment in which that system moves also seems accommodating, not completely safe, not perfectly tuned, but moderate in ways that matter. The Sun's birthplace likely lay within a stellar nursery, a cluster of siblings that eventually dispersed. Had it remained bound in a dense, long-lived cluster, the rate of close encounters would have been higher. The chance of another star passing close enough to perturb the outer solar system might have risen. Instead, the cluster dissolved, and the Sun drifted out into a quieter spiral arm segment. Our galaxy is part of a small collection of galaxies called the Local Group. It includes the Milky Way, Andromeda, the Triangulum Galaxy, and a collection of smaller dwarf galaxies. This group, in turn, sits in a larger structure of groups and clusters. But crucially, the Local Group is not an enormous, tightly packed cluster like the Coma cluster or the Virgo cluster, where hundreds or thousands of galaxies swarm together, where interactions are frequent, where intracluster gas is hot and dense. In those crowded clusters, galaxies are stripped of their gas, their star formation quenched, their orbits around the cluster center chaotic. The space between galaxies is not empty but filled with hot plasma. Any star systems moving through such an environment would live under a different set of long-term conditions than ours. The Local Group, by contrast, feels like a relatively quiet cul-de-sac on the outskirts of a large cosmic metropolis. Again, this might be nothing more than the natural outcome of structure formation. Galaxies form in dark matter halos. Some end up in big clusters. Some end up in small groups. There is no need to invoke choice. But from the perspective of a fragile biosphere on a small planet, it is hard not to notice that, by coincidence or necessity, we live in a place that is neither too hot nor too cold, neither too loud nor too silent, at scales much larger than our own solar system. You might feel, in the face of this, a kind of diffuse gratitude, not toward a named being, necessarily, but toward the fact that so many layers of environment line up in ways that have allowed complexity to persist. The Sun's spectral type and variability, the architecture of its planets, the presence and placement of Jupiter, the position of the solar system in the galaxy, the nature of the Local Group. Each layer adds its own flavor of risk and its own flavor of protection. If any one of these had been different, life might still have emerged here in some form, or it might not have. Or it might have emerged elsewhere entirely, under conditions we cannot imagine. We do not know. What we do know is that, in this particular arrangement, on this particular world, minds exist that can sit in the dark, listen to the hum of a refrigerator, feel their own heartbeat, and think about galactic habitable zones. The gardener, in this telling, is not a figure standing with a hose and pruning shears. It is a metaphor for the stacking of conditions that feel, to us, oddly hospitable. Maybe it is nothing more than chance filtered through the anthropic principle. We find ourselves in a place where life can ask questions, because only such places produce beings that ask. Maybe there are many such places, scattered through the galaxy, and we are one of countless gardens growing in similar soil. Or perhaps the combination of circumstances that led to this quiet suburb, this particular star, this specific arrangement of planets, is, in some statistical sense, rare. If that is true, then the feeling that someone chose the plot, even if that someone is only the blind selection of physics across many possibilities, will be hard to completely shake. Either way, when you open a window at night and see the hazy smear of the Milky Way arcing overhead, you are looking out into the neighborhood that has, for now, held you. A spiral arm in a moderate galaxy in a modest group. The street on which your small garden has managed, against long odds or by simple inevitability, to bloom. If space is the street our garden lives on, then time is the weather that has been passing over it since the beginning. Soft some days, brutal on others, and always moving. Planets do not appear fully formed in a single moment. They are not designed in a day. Earth, as far as we can tell, has been here for around 4.5 billion years. That span is so long that if you compress the whole history of the planet into a single year, all of human civilization would fit into the last seconds of the last day. Everything you know, every story you have ever heard, would be a faint whisper at the very end of a very long recording. In the beginning, Earth was not the stable blue world you see in photographs. It was molten. Its surface was a sea of lava, cracked and glowing, under a sky that may have been choked with volcanic gases. Asteroids and comets slammed into it with such violence that whole regions would have been vaporized. Oceans, if they tried to form, could have been boiled away again and again. The crust was thin, new, easily broken. It was a garden in the sense that there was ground, but the ground was being torn up faster than anything delicate could take root. Slowly, as the rate of impacts declined and the planet radiated away its heat, a sturdier crust formed. Volcanoes were still common, but the entire surface was no longer an ocean of magma. Water condensed and stayed, filling basins, carving early seas. The air was different from what you breathe now, rich in gases that would be toxic to familiar life. And yet, somewhere in those early oceans, or perhaps in hydrothermal vents or on mineral-rich shorelines, chemistry began to cross a threshold. Molecules that had simply existed started to copy themselves, to persist, to vary. The details of that first transition from non-living to living are still uncertain, and may remain so for a long time. What seems likely is that microbial life was present on Earth much earlier than humans once thought, within the first billion years or so of the planet's history. If you picture Earth as bare rock, then those first microbes were like the earliest moss clinging to stone. Thin films of life, feeding on chemical gradients, altering their environment in tiny ways. Some microbes evolved the ability to harness sunlight, to use photosynthesis to capture energy and release oxygen as a byproduct. Over immense spans of time, this slow exhaling of oxygen into the atmosphere changed the planet's chemistry. Eventually, this process led to what geologists call the Great Oxidation Event, around 2.5 billion years ago. Oxygen levels in the atmosphere rose significantly, transforming Earth's surface environment. For many existing organisms, oxygen was a poison. For others, it became an opportunity, enabling more energy-rich metabolisms. It was as if the moss had not only covered the rocks, but also begun to change the very air above them, preparing the soil for future growth. For long ages afterward, life remained mostly microscopic. Layers of microbial mats, colonies in the sea, tiny cells dividing and mutating. The garden was alive. But from a distance, it would still have looked like a simple, quiet world. Then, gradually, multicellular life emerged. Cells began to cooperate, specialize, build bodies together. Over hundreds of millions of years, the oceans filled with strange animals, plants, and algae. Fins and shells, eyes and teeth, coral reefs and predatory fish transformed the seafloor into a layered ecosystem. Plants colonized land. Forests spread. Insects followed. Then amphibians, reptiles, mammals, birds. Entire ecosystems formed, interlocking webs of mutual dependence and competition. The garden became not just a flat carpet of moss, but a complex, three-dimensional tangle of roots and trunks and branches and leaves, with creatures moving through every layer. From the outside, it might be tempting to see this as a steady climb upward, a smooth unfolding of complexity. Earth's rocks tell a different story. They record multiple mass extinctions, moments when large fractions of species vanished over geologically short intervals. Sometimes the culprits were volcanic outbursts that flooded continents with lava and filled the air with ash and greenhouse gases. Sometimes they were impact events, large rocks from space that slammed into the planet and triggered cascading climate changes. Sometimes, likely, they were the planet's own slow cycles of plate tectonics and ocean chemistry reaching tipping points. Each mass extinction was a hard pruning of the tree of life. Whole branches disappeared. Entire ways of being ended. But in the aftermath, surviving lineages diversified and expanded into the newly opened spaces. Mammals, for instance, had existed for a long time in the shadows of dinosaurs, small and eking out niches. When the non-avian dinosaurs disappeared near the end of the Cretaceous period, mammals diversified explosively. Forests and plains, once dominated by giant reptiles, became, over millions of years, the stage for hooved grazers, big cats, primates. Nothing about this process was gentle in the human sense. Yet, over vast timescales, it had an almost horticultural rhythm. Growth, overgrowth, cutback, new growth. The garden never settled into a final, unchanging form. It kept remaking itself. Humans, as a species, step into this story very late. Anatomically, modern Homo sapiens have existed for only a few 100,000 years at most. That is a blink compared with the age of the Earth, a thin layer of paint on a very old wall. Agriculture, cities, writing, science, industry, all of the structures we call civilization occupy only the last few thousand years. The time between the building of the first stone monuments and the launch of the first space telescopes is tiny compared with the time between the first microbes and the first forests. If there were a gardener with a goal, it would be a patient one. It would have waited through billions of years of molten rock, through countless local disasters, through multiple global resets, for nervous systems to evolve, for brains to form, for language and curiosity to arise. It would have watched crustal plates slide, mountains rise and erode, oceans open and close. It would have seen continents shatter and come back together again. Only then, in the last fractional sliver of the planet's life, would the kind of mind that wonders about gardeners appear. Of course, once you step back into a more strictly scientific language, there is no need to invoke intention. Evolution, by natural selection, operating on variation, is enough to produce complexity given time and a stable environment. Planetary geology, governed by physics, chemistry, and the flow of heat, is enough to produce continents, climates, and cycles. The gardener in this chapter is really a name for patience itself. And time is not only important here, it also matters when we look outward. Many of the stars we have surveyed with missions like Kepler and TESS are younger than the Sunday. Their planets may still be in relatively unstable phases. Orbits may be shifting. Bombardment by leftover debris may still be more intense. Tidal interactions may still be reshaping rotation and heat flows. These are young gardens, still being dug up and replanted. Even if a planetary system has the right architecture in space, a moderate star, a habitable zone rocky planet, an outer giant, it may not yet have had enough time for complex life to develop. Microbial life might arise relatively quickly, at least in some environments. But the path from single cells to beings that build radio transmitters and space telescopes seems, at least here, to require billions of years of relative stability. Strong enough change to drive evolution, but not so strong as to wipe the slate completely clean too often. Rarity, in that sense, is not only about how many such systems exist scattered through the galaxy. It is also about how many of them are at the right stage right now. A garden may be planted in many places, but only in some of them will the flowers you are looking for be in bloom at the specific moment you choose to walk by. Think of all the conditions we have talked about so far. The right kind of star, a suitable planet in the habitable zone, a favorable planetary architecture with perhaps an outer giant, a calm enough galactic neighborhood, a larger cosmic environment that is not too disruptive. Add to that the requirement that billions of years have passed without the planetary system being torn apart and without its biosphere being erased too many times. Finally, add the condition that, during the brief interval when a technological species exists, it also has the tools and inclination to look outward and ask these questions. You are living inside that thin overlap. Space and time together have conspired, or simply naturally combined, to make this moment possible. For most of Earth's history, no one was here who could have understood what a galaxy is. For most of the galaxy's history, Earth did not yet exist. For most of the universe's history, galaxies were younger, stars more violent, heavy elements rarer. Now, In this slim fraction of cosmic time, the situation is different. Stars like the Sun are common. Heavy elements sufficient to build rocky planets are widespread. At least one planet, this one, hosts a global civilization capable of building instruments like Gaia, Kepler, and TESS. Capable of turning photons into statistics, and statistics into quiet, unsettling realizations. If you lean again into the metaphor, you might ask, if there were a gardener, what would they have been waiting for? For moss to become forests? For forests to give rise to animals that can think in stories? For those animals to light up their nights with electricity, to launch metal tools into orbit, to replay the shape of their own home from a distance? There is no answer written in the sky. The universe does not annotate itself with motives. The question itself may say more about our need for narrative than about reality. But even without intention, time alone does something remarkable. Given long enough, rare events happen. Given long enough, improbable chains of cause and effect can unfold. Given long enough, a star in a quiet part of a galaxy can gather a disk of gas and dust, form planets, see life arise. Watch that life look back. From a certain angle, that is all the gardener has ever been. The name we give to time plus physics, when the outcome feels too delicate to bear being called an accident. As you lie there listening, the minutes you spend with these thoughts are almost nothing. They are less than a heartbeat in geological terms, less than memory in galactic terms. Yet you inhabit them at a turning point in our understanding. Missions like Kepler have already shown us that planets are common and that many systems look nothing like ours. TESS is adding nearby examples, bright stars whose planets we can study in more detail. Gaia is beginning to trace the invisible loops of distant giants. This convergence is temporary. Instruments age, missions end, civilizations change. But right now, in this brief overlap, you are alive, conscious. You carry in your head both the story of Earth's long, violent, inventive history and the first rough sketches of thousands of other gardens in the sky. Time has been shaping this place for billions of years. You have been here for only a fragment of a fragment, and yet, somehow, you have arrived at precisely the moment when the question of how rare our solar system might be is no longer just a philosophical musing, but something that can, at least in part, be answered with data. That coincidence of space, of age, of technology, of curiosity, is its own quiet mystery. When you sit with that quiet mystery long enough, another one starts to unfold, and this one lives not in the sky, but in the way your own thoughts arrange themselves around it. Because the moment you realize how unlikely your situation feels, a small voice inside you immediately wants to ask, then, why? There is a simple idea in cosmology that tries to answer that question without changing any laws of physics. It is sometimes called the anthropic principle, but you do not need the jargon. It says, in essence, that of course the universe you observe looks hospitable to life, like you. Because if it did not, you would not be here to look at it. It is a bit like survivors walking away from a car crash. They look back at the twisted metal and say, "It is astonishing that we made it out." They might wonder if something or someone decided to spare them. But from the universe's point of view, only those who survived are available to stand there and marvel. Those who did not are simply not part of the conversation. The fact that someone is there to feel lucky is already filtered by survival. Applied to the cosmos, the idea is similar. Out of all the possible ways matter and energy could have arranged themselves, you find yourself in one where stars exist, planets can form, chemistry can become biology, and biology can become minds. You look around and think, how strange that everything is so friendly to life. The anthropic principle quietly replies, of all the places where life is impossible, no one is there to be surprised. That can sound cold. It is not meant to be. It is meant to remind us that our point of view is not neutral. We are the outcome of the story we are trying to interpret. And because we are storytellers by nature, we often mistake that filtering for evidence of intention. There is a small place on Earth that captures this tension perfectly. It lies in Gabon, in West Central Africa, at a site called Oklo. In the early 1970s, workers at a uranium mine there sent samples of ore to be analyzed. The chemists who received those samples noticed something odd. The concentration of a particular isotope of uranium, the one used in modern nuclear reactors as fuel, was slightly lower than expected. It was as if some process had already burned part of the fuel away. At first glance, the numbers looked eerily similar to what you would expect if the ore had been through a nuclear reactor. Ratios of isotopes matched what engineers see in spent fuel from power plants. That raised unsettling questions. Had someone, sometime in the distant past, used this deposit as a reactor? Was there some evidence of an ancient civilization hiding in the rock? The answer, after careful investigation, turned out to be stranger in a quieter way. About 2 billion years ago, conditions in that deposit were just right. The concentration of uranium was high enough, groundwater flowed through the rock at the right rate. Natural nuclear fission reactions could start, heat up the water, boil it away, slow down, cool, and then start again, in cycles. Oklo had been, for hundreds of thousands of years, a natural nuclear reactor running without any engineers, without any concrete walls or control rods. If you did not know that such a thing was possible, if you simply saw the isotope ratios, you might be tempted to call it proof of design, a sign of a gardener. Instead, it became a lesson in humility. Nature can, under the right conditions, build something that looks engineered, purely through the blind alignment of physics and geology. Oklo is a small, local story, but it sits in the same family as many larger surprises in science. Moments when reality revealed that it was under no obligation to match our expectations. Think of the hot Jupiter around 51 Pegasi forcing planet formation theories to bend. Or think of what happened in the late 1990s, when two teams of astronomers measuring distant supernovae found that the expansion of the universe is not slowing down under gravity's pull, but speeding up. They expected one shape for the history of cosmic expansion, and they found another. That discovery, announced in 1998 and later honored with a Nobel Prize in Physics in the second decade of the 21st century, introduced the idea of dark energy into mainstream cosmology and rewrote the standard picture of the universe's fate. Each of these moments carries the same quiet message. The universe is under no contract to keep our stories comfortable. Faced with that, humans do what we have always done. We reach for meaning. We are very good at connecting dots, at stitching events together into arcs that feel like narratives. It is a survival skill. Seeing patterns helps us predict where prey will run, where storms will move, when seasons will change. The difficulty is that this skill does not turn off when we are dealing with randomness. We see faces on the surfaces of planets, animals in the shapes of clouds, significance in coincidences that may be nothing more than chance plus attention. The Cosmic Gardener is one such story. You can take a long list of facts: the sun's stability, Earth's position, the moon's effect on tides and tilt, Jupiter's protective and dangerous role, the quiet neighborhood, the age of the galaxy, the timing of Gaia's mission, and arrange them like stepping stones. From a certain angle, they look like the work of a curator, someone or something that prefers long-term stability and gentle chaos, just enough to grow minds and not enough to erase them. There is a risk in this. If you lean too hard into the gardener idea as literal truth, you can begin to force every new piece of data into that frame. Contradictions are brushed aside as mysterious ways. Observations that point to a more mundane, probabilistic explanation are ignored. Every apparent coincidence becomes another brick in a structure you have already decided to build. That is how stories harden into dogma, not just in religion, but in every area of life. Conspiracies work like this. So does the stubborn refusal to update a theory in the face of evidence. Too much belief, held too tightly, can make us blind. Yet there is also a gentler way to hold the gardener idea, not as a claim about what the universe is, but as a metaphor for how it feels to live inside a planetary system that seems, the more we learn, a little too calm for comfort. In that softer view, the gardener is simply a lens. A way to talk about the fact that we inhabit a place where conditions have been good enough for long enough that we now carry enormous responsibility. If this garden is rare, then the lives within it are rare. If it is common, then we are part of a wider pattern that deserves care rather than contempt. Either way, the metaphor nudges us toward stewardship, toward treating our planet not as a disposable resource, but as a fragile, contingent arrangement of improbabilities. Art has been playing with versions of this metaphor for a long time. You can see it in films like Interstellar, released in the middle of the second decade of the 21st century, where mysterious they seem to bend gravity and time to help a dying civilization, only for the story to loop back on itself in a more human way. Or in Contact, from the late 1990s, where patterns hidden in radio noise hint at a message and force humanity to question what counts as evidence, what counts as faith. These stories are not scientific arguments. They are thought experiments turned into images and music. They give shape to feelings that are hard to express in equations. The sense of being guided, abandoned, chosen, or alone. They show how often we return, in different clothes, to the idea that maybe there is someone in the garden with us, even if that someone turns out to be ourselves from another time. The balance, if we want to stay honest, is to let data do what data does best, and let imagination roam where data is silent, without confusing the two. On one side, there are hard numbers and models. Kepler's statistics on planet sizes and orbital periods. TESS's catalogue of nearby systems. Gaia's astrometric wobbles. Simulations of protoplanetary disks evolving under gravity and gas flows. These anchor us. They tell us which planetary architectures are common and which are not. They show us that hot Jupiters and compact multiples are real, not rumors. They let us estimate probabilities. On the other side, there are the gaps. We do not yet know how many true solar system twins exist. We do not know how often complex life arises even in favorable conditions. We do not know how long technological civilizations tend to last. In those unlit rooms, imagination will enter whether we invite it or not. The best we can do is keep reminding ourselves which parts of the house are lit by data and which parts are lit by candles we are holding ourselves. In that divided light, each listener will, inevitably, carry their own version of the gardener. Some will hear this and think of God, by whatever name they know. They will hear the stacking of coincidences, the apparent just rightness of so many parameters, and feel that it resonates with their existing faith. For them, the gardener is not a metaphor but a presence, and the science only deepens their sense of wonder. Others will hear it and think of physics and probability, of multiverse hypotheses and selection effects. They will say that given enough regions of space, or enough cycles of cosmic birth and death, some pockets will look like ours. And of course, we find ourselves in such a pocket. For them, the gardener is simply the nickname we give to statistical flukes that happen to talk. Still others will be wary of the whole frame. They will see in the gardener language a kind of poetry, valuable as a way to talk about fragility, but not something to lean on too heavily. For them, calling gravity and time a gardener is interesting, but no more literally true than calling evolution a blind watchmaker. Useful as metaphor, dangerous as ontology. All of these responses are human. All are ways of trying to place ourselves in a story that is, by its very nature, vast and indifferent. The important thing, for our purposes here, is not which version you hold. It is that you remember where the story ends and the data begin. That you allow the gardener to be what it has been throughout this journey. A figure walking at the edge of the frame, never fully stepping into focus. Because soon, missions like Gaia will deliver more of their harvest. Papers will be published with estimates of how rare systems like ours really are. There will be headlines. There will be plots shared on social media. Some people will feel vindicated. Others will feel shaken. The temptation to say, at last, this shows we were meant to be, or this shows we are just one accident among many, will be strong. This script will not go there. The gardener will not be declared real or declared an illusion. The numbers will come, and they will refine our sense of how unusual our solar system's architecture is. But the final turn, where you decide what that rarity or commonness signifies, cannot be printed in a journal article or announced at a press conference. It lives in a quieter place. It lives in the moment after the video ends, when the room is dim, when you have set your phone aside or turned off your screen, when the images of stars and orbits and wobbles are still cooling in your mind. In that silence, with only your own breathing for company, the gardener, whatever that word means to you, will either feel present or it will not. And that answer has always belonged to you. And while that answer sits with you, undecided and entirely your own, something else is happening far above the ceiling, beyond the clouds, beyond even the atmosphere that holds your breath in. The instruments we have placed there are quietly getting ready to speak. In the next few years, Gaia will release more of its measurements in what astronomers call Data Release 4, followed later by Data Release 5. Each release is not just a bigger table of numbers, it is a refinement of how sharply we can see the tiny loops that stars trace in the sky. Alongside Gaia, the transiting Exoplanet survey satellite continues to watch for shadows of planets crossing bright, nearby stars. New radial velocity instruments on large telescopes are listening even more sensitively for stellar wobbles along our line of sight. Put together, these efforts mean that for tens of thousands of planetary systems, we will soon know both the inner layout and the outer scaffolding. We will see where small, probably rocky planets hug close to their stars, and where distant giants patrol the outskirts. For many sun-like stars, we will be able to say whether there is a temperate world and whether there is a Jupiter like Guardian farther out. At that point, the question that has been haunting this whole journey can finally be turned from a story into a statistic. Does the architecture of our solar system repeat often, or does it appear only rarely? One scenario is that, once the dust of analysis settles, we find that the pattern we call solar system-like is not uncommon. Not dominant, perhaps, but robust. Hundreds, maybe thousands, of sun-like stars might show evidence of at least one small planet in the habitable zone and at least one distant giant with a mass and orbit not too far from Jupiter's. In that case, our garden would be one type among many. The universe would turn out to be quite good at building this layered, stretched arrangement. If that is how things fall, it does not make life here less precious. You do not become less unique as a person just because there are many other people. But it does change the felt shape of the galaxy in your mind. Instead of seeing the Milky Way as mostly filled with wild, alien yard designs and only a few quiet plots like ours, you could imagine it dotted generously with similar gardens. Some could be sterile. Some could host only moss and microbes. Some might have reached their own versions of forests and cities. Some might already be empty again, their flowers gone. In that world, the gardener, as metaphor, becomes a symbol for a generous universe. Not necessarily kind in the moral sense, but prolific in the architectural sense. Whatever combination of physics and initial conditions builds solar system-like layouts would be something the cosmos does regularly, not as a rare experiment, but as a common refrain. Another scenario is that the opposite happens. That, after combining Gaia's wobbles, TESS and Kepler's shadows, and years of radial velocity data, astronomers find only a handful of systems that truly resemble ours in the specific way we have been talking about. A sun-like star, a long-lived habitable zone rocky planet, a distant, roughly Jupiter-mass giant in a nearly circular orbit, a layout that is not just similar in broad strokes, but close enough in dynamical behavior to suggest similar long-term stability. If that is the outcome, then the feeling we have been circling around this whole time intensifies. The gardener metaphor gains weight, not because it becomes literally true, but because the pattern we live inside would be, in a strict statistical sense, hard to get. The chain of events that led to our solar system's architecture would look nearly unrepeatable across the sample of systems we can see. The quietness of our garden would become less like one style among many and more like an eccentric house on a street lined with very different facades. In that world, Every sunrise on Earth would carry a different kind of burden. You could look at the light spilling over oceans, forests, cities, and know that, in the galaxy you inhabit, there are very few places where that exact combination is happening. Every genome, every language, every recorded song, every unrecorded laugh would be, quite literally, part of a small, fragile set of outcomes. There would be nowhere else in the Milky Way quite like this, in layout and in history. Even if there are planets and lives in great number, between those scenarios, it is natural to wonder which one you should hope for. A crowded sky full of look-alike gardens, or a cosmos in which your home is something like a once-in-a-galaxy alignment of circumstances. Beneath that wondering lies a subtler point. Both possibilities converge on the same quiet truth. Rarity lives inside our minds as much as in the stars. For most of human history, people lived under a sky without statistics. There were myths and guesses, but no data about how common planets are. How many stars have worlds? What kinds of architectures exist? The solar system was the whole story. Now, in this narrow window of time, you carry in your head not only those myths, but also histograms of exoplanet sizes, distributions of orbital periods, models of planet population demographics. That alone is astonishing. You do not need the universe to be one way or another for that fact to matter. Whatever Gaia and its siblings ultimately reveal, the ability to frame the question in terms of numbers is a privilege layered on top of all the other coincidences we have talked about. You are one of the very few generations of humans who will see this shift from speculation to survey. And what of the gardener in these two futures? If solar system-like architectures turn out to be common, the gardener becomes a symbol of repetition, a way of saying that the laws of physics, given disks of gas and dust around stars like the sun, often carve out similar safe harbors. The gardener is then not an artist making one unique masterpiece, but a pattern stamped again and again across the galaxy, like leaves sharing the same underlying symmetry. If they are rare, the gardener becomes a symbol of fragility, a name we give to that chain of low-probability events that somehow did not break, did not reset too often, did not derail the emergence of minds. The pruning in that case would be not only physical, the migrations of Jupiter, the clearing of belts, but historical, the avoidance of catastrophes at certain key moments, the survival of certain lineages, the improbable endurance of a species that can destroy its own garden and has not yet fully done so. In neither case does science step over a certain line. Telescopes and analyses can tell you how often a certain architecture appears. They can give you error bars and confidence intervals. They can compare theoretical models with observed distributions. They can say, with increasing clarity, whether our solar system is statistically unusual in this particular sense. They cannot tell you what to do with that information at midnight, lying in your bed, listening to the faint sounds of your own life. They cannot tell you whether to feel chosen or accidental, consoled or unsettled. They cannot tell you whether to call the pattern God, or nature, or nothing at all. Those are questions that live in philosophy, in religion, in art, and in the private space of your own thoughts. So, at the end of this long walk through numbers and metaphors, there is only one small invitation left. After this episode ends, let the analysis stop for a while. No more distributions, no more scenarios. Instead, picture the solar system as if you were outside it. See the sun as a small, bright bead in the arm of a quiet spiral galaxy. See the planets as faint rings of light around it, almost invisible at that scale. One of those rings holds a rocky world with oceans, continents, clouds, cities, and you, listening. Let that image sit. Tonight, as you close your eyes, Gaia's data is still being decoded somewhere in a room lit by screens. Stars are still wobbling in the dark, whether or not anyone is measuring them. Planets are still turning, carrying deserts and storms, and maybe forests, and maybe nothing at all. Whether the solar system is rare or not, you are still lying inside this particular garden, under a thin canopy of air, at a distance from your star that happens to be just right for liquid water and for questions. If you like, you can let that awareness change the way you look at your own sky tomorrow. Maybe you step outside for a moment, find a patch of darkness, And remember that you live in a place that might be one among many, or one among very few. Maybe you choose to treat it a little more gently. And maybe, just before sleep pulls you under, that is enough to whisper a quiet thanks to a real gardener, if you believe in one, or simply to the universe itself for allowing such a garden to exist at all, and for allowing you, for a brief time, to be awake inside it.